Hello everyone. Today we will be going over operational amplifiers or op-amp filters. An op-amp is a neat little component with a variety of uses. What makes an op-amp so neat? Well, there are a few advantages to the op-amp compared to passive circuits, which just use the resistor, the capacitor, or an inductor. An op-amp is an active component, which means that it can introduce or add energy into the system. Before, with a passive circuit, we had our output voltage much smaller than our input voltage, or at best equal to our input signal. But now, for any frequency, our op-amp can give us, if we wanted it to give us a higher output voltage. Not only that, the op-amp is made in such a way that our output impedance does not change this property. That is, we could still have a higher output voltage for any frequency we introduce to it. Ideally, our op-amp would have these set of characteristics. Realistically, it falls short of this by a lot, but it still gives us a plenty large gain, impedance, and so forth. And this is what makes the op-amp great. Well, great at what it is made to do, which is to give us a very, very large gain to our output, which is okay. For now, that seems pretty limiting. However, when we add in a feedback loop, the story changes a lot. Consider this inverting amplifier. It's inverting since our input voltage is on the negative terminal of this op-amp, and the positive terminal goes to ground. To analyze this circuit, we need to look at the nodes, or where each component connects to one another. So we will start by looking at that node where the input signal goes and gets connected to the first resistor, the VA node where both resistors connect to the negative terminal of the op-amp, the ground node where our positive terminal of our op-amp and our input connect to ground, and our output node where our second resistor connects to the output of our op-amp. Now, most of these are something we already know, and the out's the one we're trying to find. So we already know the first node because it's our input voltage. We know what our input signal would be. We already know ground because it should be our reference node, or where we consider it to be 0. And we also are already trying to find out the out, so this one's already also pretty straightforward. So the one we're really concerned is this VA node. Okay, we're going to be using Ohm's law, or a variation of it, where we know that the current is equal to voltage over resistance. And we're also going to be using Kirchhoff's current law, which all that means is at any point in this circuit, you won't have current just growing uncontrollably or getting sucked in uncontrollably. Current's always flowing like a river. It's not going to stop at one place and just increase for and always, right? So all currents going through this VA node should cancel out, right? Some of them should go in and some of them should be going out, and the ones that are going in and going out should be about the same amount. Or it should be the same amount. So putting it together, our current coming in from the input, going to the op-amp, and going out to the output voltage should all add up to 0, because we don't have any current just staying at that one spot. Knowing that, and using the Ohm's law we just discussed previously, we could replace all those currents with voltage differences over the resistance. So the current that's coming from the input is the voltage of VA minus our input voltage all over the resistance 1. Current going through the output is the voltage of VA minus the output voltage all over R2. The current going through the op-amp is the voltage of VA over the resistance of the op-amp minus the voltage in the op-amp. So, an op-amp ideally is made to find the difference between the positive and negative terminal, but you could also think of it as trying to make them be the same. So if we look at the positive terminal, we know it's completely going to ground. So the voltage of VA is 0, and therefore the voltage across these two terminals should be pretty much the same, and it should be 0. So we could eliminate that part of our equation, and we're also going to put that in for the rest, because again, VA should be mimicking the ground node. So we now have negative V in over R1 plus negative V out over R2. Let's go ahead and solve and separate those two, and now we have negative V in over R1 is equal to V out over R2. Solving for V out, we have negative V in times R2 over R1. Or if we want to look at the gain of this amplifier, because it is an amplifier, we will divide by V in to see how many times larger V out is compared to V in. So we have V out over V in, which is equal to negative R2 over R1. And as you can see, we have a negative because we do have an inverting amplifier. So it's basically flipping everything, sort of like in math class where you talk about flipping over the x-axis. Now, notice how it's completely dependent on just R2 and R1, which means if we make R2 larger than R1, we would have a gain, a very big gain, and we have free range of these two variables, so we could make any gain we want now. V out over V in is also sometimes called the transfer function. Let's take a look now at a low-pass filter. We have pretty much the same idea as before. We want to look at that one node again. And just like before, we're going to be doing node voltage. So we're going to go through all those. This time, however, we're going to use the impedance. Now, impedance is just the same thing. It's similar to resistance. However, this time we are taking into account the apparent resistance used by our capacitor or our inductor if we had one. So here we have pretty much the same first two steps. We have VA minus V in over Z1 plus VA minus V out over Z2 plus 0, which should equal to 0. And we could continue to solve for this, and we know that VA should be pretty much the same thing as the positive terminal, which is ground. So we're going to 0 that out. And we're going to continue to solve for V out just like before. And we have V out is equal to negative V in times the impedance times the output impedance divided by the input impedance. Or in other words, we could see the gain of this low pass filter by dividing by V in. So we have V out over V in is equal to the negative output impedance divided by the input impedance. So very similar to before, we just need to do a few more steps to figure out these impedances. So let's start with the easy one, the input impedance. Well, that's just the first resistor, and that's just like before, we know what that is. It's just R1. The feedback impedance, or the output impedance like I've been calling it, is the parallel connection between R2 and the capacitor. Now the capacitor has an apparent resistance or an impedance of 1 over J 2 pi Fc. The J or I is just indicating us that this is a imaginary value or an impedance, not a resistance. The 2 pi F tells us that this is the largely dependent on the frequency of our input, and the C is our capacitor value in farads. Now we're gonna try to find what this impedance would be, and we know whenever we deal with a parallel circuit, we have to take the inverse of each component, add them together, and take the inverse of that. So we have 1 over R2 plus J 2 pi FC. Adding these two together, we get 1 plus J 2 pi FC R2 divided by R2. Now we could do our final inversion, and we get our feedback impedance is R2 divided by 1 plus J 2 pi FC R2. Great, now we could put what we found for our second and first impedance, and putting it all together, we have negative R2 divided by R1 times 1 plus J 2 pi FC R2. And this is how we'll leave it for now. We do know that we have a J or an I on the denominator, but for now we'll leave it as such, because this tells us already quite a bit of our filter. If you notice, we again have negative R2 or R1, which happens to be our gain, and we have the 1 over 1 plus J 2 pi FCR2. That first part just happens to be our gain. Unlike before with just a capacitor and resistor, this now can be much larger than our input. And this second part would be our filter. This will tell us exactly where our filter will start acting upon this circuit. If our frequency is low or close to 0, we can see that this just becomes 1 over 1, which means the gain is the only part to this filter, and we pretty much have a nice and large output. However, as the frequency increases, the denominator of this part increases, and this starts making it get closer and closer to 0. So the higher the frequency goes, the closer to 0 it goes. Which brings us to talking about where exactly or how exactly would this occur. Well, we always want to talk about where we would find the cutoff frequency. The cutoff frequency occurs where we happen to go negative 3 dB below our original gain, or where we are at half power for this circuit. Once we are at half power, this circuit starts losing a good part of its signal. So that is where our cutoff frequency will be at. And for this circuit, for this example, it happens to be right where that red line's at. Okay, we took a look at a low pass filter. Now let's take a look at a high pass filter. Again, we're going to do an inverting one. And again, we will be looking at that VA node. So this starts out pretty similar as before. We look at that node and we do our node voltage. We do VA minus VIN over the impedance there, plus VA minus Vout over the impedance in the feedback loop. We already know that VA is 0, so we'll plug that in. And we solve for Vout just like before, and we would end up with Vout divided by Vin is equal to negative Z2 over Z1. So this is a very similar equation, or actually the same equation as our low pass filter. However, we still need to calculate once again for these two impedances. So let's start with the easy one. The feedback loop is just the second resistor, so that's easy. The first impedance is a series connection between the first resistor and the capacitor. Again, the capacitor has an impedance of 1 over J 2 pi FC. If we want to combine those two, we're going to have a common denominator. So if we do that, we're going to end up with 1 plus J 2 pi FCR1 over J 2 pi FC. So now we could plug that in for Z2 and Z1, and we will get the following. Vout over Vin is equal to negative R2 times j2 pi fc divided by 1 plus j2 pi fc r1. Really similar to the one for the low pass filter. However, we do have the j2 pi fc on top as well. Well, just like before, our gain would be that negative R2 over R1, and our cutoff frequency will be based off the part on the denominator. If you notice in this case, when we plug in a small frequency, the bottom would still go to 1, but the top, since it's multiplying, will have also a very small number. So for very low frequencies or zero frequency, this would be very low or non-existent. For higher and higher frequencies, the frequency on top, the F on the top and the F on the bottom, happen to be similar and cancel each other out, getting us closer and closer to that negative R2 or R1 gain. So we can see a Bode plot for this too, which shows the frequency response of this circuit. As you can see in this case, the magnitude gets higher and higher as our frequencies get larger and larger. Alright, now let's go ahead and do some practice problems. Our first practice problem is find the gain of the given diagram. We can see here that this is just op-amp amplifier, so we can do what we talked about just recently. And we won't go through that again. I'll just put it all here. So what we really want to do is just figure out that this is the correct diagram for our inverting amplifier. And once we do that, we just need to plug in the values for R2 and R1. So really all we're just concerned is figure out what negative R2 over R1 would be. Plugging in those values, we get negative 50,000 over 2,000, which ends up being a gain of negative 25. And we can also figure out the output voltage by plugging in our input voltage, and we will get an output voltage of negative 125 voltage. Now this would be true if the source voltage of the op-amp is that big, otherwise it will cut off near the source voltage of the op-amp. Question number 2. Find the cutoff frequency of the low-pass filter shown below. We've gone through this already, and we know that our equation should be negative R2 divided by R1 times the quantity of 1 plus J2 pi FC R2. We can plug in our values for R2, R1, and C, and we get negative 10,000 divided by 1,000 times 1 plus J2 pi F times 0.1 microfarads times 10,000. Simplifying that all out, the 10,000 divided by 1,000 becomes just negative 10. 0.1 microfarads times 10,000 ohms ends up combining to be 0.001. And we have our equation here. Now, to solve for the cutoff frequency that we want, we're going to use just a part of this equation, namely 1 over 2 pi times 0.001, everything right next to f. And if we calculate for that, we will end up with a cutoff frequency of 159.15 hertz, about 160 hertz. And here we can show it in the Bode plot, and the red line shows exactly where our cutoff frequency would be at, which looks to be about 160, as we've said before. Our third problem is find the cutoff frequency of the high-pass filter shown below. Our high-pass filter would have the equation of negative z2 over z1, where z2 and z1 were given to you before, so we could plug all that in, and we get negative R2 times J2 pi FC divided by 1 plus J2 pi FC R1. Plugging the values that we know, we have negative 10,000 times J2 pi F times 0.015 microfarads, all divided by 1 plus J2 pi F times 0.001. 0.015 microfarads times 30,000. Simplifying this as much as we can, we'll get negative J 0.003 pi F over 1 plus J 0.009 pi F. The part that we're interested in is the bottom. So our cutoff frequency is 1 over 0.009 pi, which turns out to be 353.67 hertz, about 350 hertz. And we could also see this in the Bode diagram. And there you go. That's a few practice problems to get you to understand these inverting amplifiers a bit better. There are other configurations and other uses of the op-amp. We could talk about the non-inverting configurations of the amplifier, low-pass filter and high-pass filter. As you can see, the input signal or voltage is connected to the positive terminal of the op-amp, where we have the rest of the circuits connected to the negative terminal of the op-amp. For these, we'll be doing exactly the same thing as before to find the correct equations for them. I'll just show you how to go about doing this for the non-inverting configurations. So just like before, we'll talk about the nodes and we'll use node voltage, and if we do so, we'll come out with 1 plus R1 over R2. As you can see, we again have a gain or amplification of R1 over R2. There is a plus 1 there, which happens with these non-inverting configurations. And notice that the gain happens to be positive, so we'll have a positive gain this time. For the low-pass filter, going ahead and doing so the same thing as before, we notice that it's rather similar to the amplifier, so we could start off with trying to find the two impedances. And just like before, the two impedances would be pretty similar to something we've done before. So our answer should be 1 plus R2 divided by R1 times 1 plus J2 pi FC R2. Rather similar to the one before, except where there is again a positive here instead of a negative. A high-pass filter happens to have a similar story, and our answer turns out to be 1 plus J2 pi FC R2 divided by 1 plus J2 pi FC R1. And that's it. Thanks for watching. Comment, like, and subscribe. And always keep learning. If there is any questions about this, please make sure to put it down in the comments down below. And watch out for any other videos. There is plenty more uses for the op-amps, which I might do next. Thank you.